Hello everyone, this is our class number 5. We are going to do a quick crash course in statistics and probability. I'm going to do it in two parts. The first part is mostly theory, and the second part we are going to apply everything we learned in the first part in R. All right, so let's begin. And the goal, the end goal for this part is to understand what is this slide. This is the last slide that we're going to cover, but the goal of reviewing the statistics part is that how we can read these things. So for instance, what does independence mean? What is mean independence? What is conditional probability, conditional expectations? So if you're already familiar with these terms, you can go ahead and skip this lecture video. But if you feel the need that, okay, you need a refresher on the definitions of conditional expectation, conditional probabilities, and correlation and things like that, so make sure that you watch this video very carefully, because these are the terminologies and things that we are going to use extensively in econometrics. Okay, so you should not skip this couple of videos if you need a refresher for your business stat. Okay, so let's start by reviewing some basic definitions. Okay, so we start by definitions of experiments and then random variables and what is PDF and CDF. So experiments by definition, it means that it's any procedure that can be infinitely repeated and has a well-defined set of outcomes. So there are two things that are important here. First of all, experiment must be infinitely repeated. You should be able to repeat it for infinite number of times, and more importantly, the outcomes are very well defined. So let me give you a bunch of examples in terms of experiments. So for instance, flipping a coin, right? You can flip a coin multiple times, and the set of outcomes is very well defined. So if I flip a coin once, what is the set of outcome? Head, tail. Rolling a dice, what is the set of outcome? 1, 2, 3, 4, 5, 6, right? And these are type of discrete examples. So let me give you a bunch of continuous examples. For instance, collecting data on household wage, right? I can infinitely repeat these experiments, collecting information on people's wages, right? And what is the set of outcome? It's very well defined, right? The income has a minimum number. So again, let's say you're talking about the hourly income. So maybe the minimum wage is the minimum number. And the maximum one, well, we know that practically it can be millions of dollars, but there's an endpoint to that, right? It's not unlimited. So the set of outcome is very well defined. So this is experiments. Now we move on to random variables. What is random variable? A random variable takes on numerical values. So a random variable is a variable that takes on numerical values, and the outcome is determined by experiment, right? So I'm going to, in the whiteboard, I'm going to give you a bunch of examples of experiments and what are the random variables. But before that, let's figure out what are these two other terminologies, and then I'll move on to the whiteboard. So we have discrete random variable versus continuous random variable, right? So what are the examples for discrete random variables? The ones that take integer numbers, right? Like number of heads in a coin flipping experiment, number of times observing a 4 when you're throwing a dice, right? So it can be, if you throw a dice, I don't know, 10 times, and you're counting how many 4s it was there. So it's an example of discrete random variable. For example, your letter GPA, the number of bedrooms in a house, and the number of stocks in a portfolio, and etc., right? So the one that might be a little tricky is the letter GPA. So you might say that, okay, you said a random variable is a variable that takes numerical values, but letter GPA is letter. Remember, from statistics, we can have categorical variables, and then, for instance, letter GPA is A minus, B plus, B minus, and etc. You can assign some numerical numbers to them as well, right? So you can perfectly do that. So for that reason, we can still call it a random variable. But letter GPA is an example of discrete random variable. However, numerical GPA, So for instance, you're looking at your GPA goes from 2 maybe to 4. So it's an example of continuous random variable. What are other examples of continuous random variables? Theory. Most of the variables that you're going to work with in this course and in real world are usually continuous random variables. What are some examples? Height, weight, time, distance, numerical GPA, GDP, interest rate, price, and you name it. Wage, age, education, all these things. Well, maybe education is discrete depending on how you're defining the education, but it's discrete. But all the others are continuous random variables, right? Okay. So before jumping into the definition of PDF and CDF, let me walk you through one example that you're going to apply all these definitions to that example, and hopefully it will stick to your mind that what is experiment, what is random variable, how we calculate PDF, CDF, how we draw the PDF, CDF for both a continuous random variable and a discrete random variable. All right, so let me pull up my whiteboard. Okay. So imagine the experiment is, let me use another color. Imagine the experiment is flipping a coin twice and counting the number of heads, okay? So I want you guys to make notes with me. This is one of those lectures that needs your 100% concentration. So I highly recommend you to grab a pen and piece of paper and pause the video when I ask you a question. Try to come up with the answers on yourself, by yourself, and then hopefully you can follow the lecture more carefully, because again, this is one of the few lectures that we do in the class that it's more math extensive and it really needs your concentration. Okay, so imagine the experiment is flipping a coin twice and count the number of heads. Remember, what was the definition of experiments? You should be able to infinitely repeat the process. Yes, you can infinitely repeat flipping a coin twice, right? And the set of outcomes must be very well defined. So if I'm flipping a coin twice and count the number of heads, let's look at that. So what is the set of outcome? It can be, remember, we are flipping it twice. It can be head, head, right? It can be head, tail. It can be tail, head, and it can be tail, tail, right? So my set of outcomes is 4. And, I have 4 different outcomes, and it's perfectly well defined for this specific experiment, right? Now let's move on to a random variable. So imagine we are going back to the definition of random variable. It's a variable that takes on numerical values, and the outcome is determined by experiment. So I have to assign some numbers to these outcomes, right? So that's the goal, random variable. And let's give for this random variable, let's give it a name. Let's show it with capital X. And by the way, capital letters are reserved for random variables, and small letters are reserved for the values for random variables, right? So for instance, here the capital X is my random variable, and I can show the values that this random variable take with small letter x, okay? So again, this random variable is defined as we need to assign some numerical values to this experiment, which is flipping a coin twice and count the number of heads. So I want you to pause the video and think about it. What is the value of x for the first observation? We are counting the number of heads. There you go, 2. What is the value for the second outcome? 1. What is the value for third outcome? 1. What is the value for fourth outcome? 0. Does that make sense? So these 0, 1, and 2, we show them with little x. So these are the values of random variable x. So x can be either 0, 1, or 2. So little x can take 3 values, 0, 1, 2. So guys, this is important. I want you to pay attention and make sure that you get the terminology and distinction between small letters, cap letters. This is pretty standard in the statistics world. So again, small letters are the values that we assign to random variables, and cap letters are the random variables themselves. So let's say that I define this random variable x, and x can take 3 numbers, 0, 1, 2, right? Now let's move on and talk about a PDF and CDF. So going back to slide, what is PDF? PDF is the probability density function, right? So probability density function, it summarizes the probabilities of outcomes, right? So let's go back to the whiteboard. We need for something that summarizes the probabilities of outcomes, right? So if I ask you, what is the probability of seeing, let me use an autocolor. What is the probability of seeing this number? Remember, how many outcomes I have? 4. So what is the probability that I see this outcome, head? There you go, 1/4, right? So the probability is 1/4. What is the probability that I see only one head? Think about it. So I can see one head here, I can see one head here. So what is the probability? 2/4, right? And what is the probability that you observe 0 head? Yes, that's 1/4. So as you can see, PDF is some function that summarizes the probabilities of outcomes, right? So I know what is outcome, I know what is random variable, and now we know what is PDF. And we show PDF with small little f of x. Okay, so we use little f for PDF and capital F for CDF. So we're going to talk about this one, capital F for CDF. Okay, these are some standard notations that we use in statistics. Okay, now that I know what is PDF, let's look at how we can define the CDF. Okay, so the CDF is defined as it's a function that summarizes the cumulative probabilities of outcomes, right? So we are looking for something that summarizes the cumulative probabilities of outcome. Okay, let's go back to our slide here, our whiteboard. But before that, let me plot the PDF because it makes a lot more sense if I plot the PDF first and then we go to CDF. Look at the cumulative probabilities. Okay. So I'm going to plot the PDF here using black. On the horizontal axis, I have my x variable, which can take three numbers here, 0, 1, 2. On the vertical axis, I have my little f of x, and we also show it with probability of x as well, little p of x. Okay, so probability of x. Okay, and for the sake of illustration, let me start 0 from here. So 0, 1, and 2, right? So what is the probability that x is equal to 0? And remember, this is little x is equal to 0, little x is equal to 1, and etc. So what is the probability that x is equal to 0? 1/4. So that's the probability. Let's say this is 1/4. What's the probability that x is equal to 1? 2/4. Let's say this is 2/4. And what is the probability that x is equal to 2? There we go. It's 1/4 again. So this is the PDF of our random variable. And here's a question for you. The random variable x, is it discrete or continuous? Yes, it's discrete, right? Because it can take discrete outcomes, right? So for instance, we are flipping a coin. So what is x here? 0, 1, 2. It doesn't make sense to see 1.5 head, 1.5 tail, right? So it's discrete. And the PDF of a discrete random variable looks like this. So usually it looks like this. And then if your x random variable has many outcomes, so you can imagine, you can simply extend this to many discrete bars put together. We call it a probability density function, right? So this is for the discrete version. I'm going to go ahead and show you the continuous version as well, just for your reference. So if you have a continuous random variable, let's say, for instance, I have a random variable w, and w is continuous. Okay, so here is my w, and here is my f of x. Oops, it's f of w, right? F of w. So you have seen this before. So for instance, this is an example of PDF, probability density function of a continuous random variable. And the PDF is also continuous, right? So the green one is the continuous, the green one is, yeah, continuous random variable. The black one is a PDF for the discrete random variable, right? Now we know that what is PDF, let's talk about CDF, right? Remember, so in this example, because, so I go from 0 to 1, I'm gonna start from here, okay? It's cumulative distribution, cumulative probability of outcomes. So when our x is equal to 0, what is cumulative probability distribution, or the cumulative probabilities of outcomes? It's again 1/4. Look at the PDF here. Look at this graph again. When x is equal to 0, what is probability 1/4? When x is equal to 1, what is cumulative probability? So it means that you have to add the probability when x is equal to 0 plus the probability when x is equal to 1, right? So it's 1/4 plus 2/4, so it's 3/4. Does that make sense? So let me open up this one for you. This is, we show it like this, capital F or CDF, and this is example 1. It's equal to the PDF, the probability, little f, of our x less than or equal to 1. So what are x less than or equal to 1? It's equal to probability. So for this one, it's a discrete random variable. It's a probability that x is equal to 0 plus probability that x is equal to 1. So I know that this is 1/4, this is 2/4, so I get the 3/4, right? And as you can guess, what is the cumulative the probability when x is equal to 2 here? What's the answer? So we get 1/4 plus 2/4 plus 1/4 again when x is equal to 2, so the answer is going to be 1. So this is not coincidence. When your random variable is discrete random variable, the CDF of the last observation, of the largest observation, is exactly always equal to 1. So the cumulative distribution function will add up to 1 for discrete random variable, okay? Now, how does the CDF look like for both discrete and continuous random variable? I'm going to use a red color, and I'm here looking at this. I'm going to show the CDF. I'm going to plot the CDF right on top of this this PDF, right? So we'll see when x is equal to 0, the CDF is also equal to 1/4, right? Anything below 0, CDF is 0. If CDF is x is exactly equal to 0, CDF is 1/4, right? Now, if x is equal to 1, if x is equal to 1, then what is CDF? What do you think? We already calculated. It's 3/4, right? So let's say 3/4 is here, right? And when x is equal to 2, so this is 3/4, and this is 1. There you go. So the red curve is our CDF. We show it with capital F or CDF. The black one is our PDF. We show it with little f. So we already have it there. Does that make sense? Okay. Now let's look at a CDF for a continuous random variable. So for a continuous random variable, CDF, let me use another plot. I could have plotted on top of the green one, but I just wanted to make sure that you don't confuse it. So there's W here. I have capital F of W. So again, it always starts from 0, because when your random variable is 0, there's nothing the probable below that variable. So we start from 0. Oops. And it will converge to 1. Okay, remember, this is continuous random variable, and then we're going to say that if eventually the cumulative probability will converge to 1. And one last thing I want you to remember from your statistic is that the area under the PDF is equal to CDF, right? So CDF is also defined as the area under PDF. So what does it mean? It means that if usually it makes more sense to, wait, yeah, this is a C, I don't know how to, yeah, let's see. I don't know why it doesn't erase it. Anyways, CDF, just ignore this one. It makes more sense to look at the area under the curve for the continuous version. So let's look at the continuous version. So for instance, in this green graph, if I look at the shaded area below the graph, I'm calculating the CDF. Okay, so we're gonna come back to this because I know I need to know the shape of the distribution and then use some formulas to calculate the CDFs. But that's not the purpose here. So we're gonna come back to this example, I think, in the beginning of the next class, and we will see how hard is it to calculate these things manually, but we never do these things manually. We're gonna use R, and R is going to calculate, do these integrals for us and calculate the areas under the curve for us. Okay, so this is the first part. We know what is experiment, what is random variable, what is probability density function, and what is a cumulative distribution function. Okay, now let's move on to some other terminology. And by the way, guys, these are some separate standalone definitions that you might think that, okay, what is the connection between first slide and second slide and third slide? Remember, the end game is to be able to interpret the last slide of this series, right? So which was independence will lead to mean independent will lead to correlation is equal to 0. Okay, so if you feel that, okay, these are some arbitrary definitions, they're not exactly arbitrary, but we need to know them one by one before we get to the last slide. All right, so let me pause the video here, and I'm going to start the conditional probabilities in the next one.